And he's a lecturer at this university in computation science. And besides being a very bright person, I had the pleasure to stay with him for 3 weeks, 5 years ago. And I can say to you that you can talk with him about anything in the world. Okay. So let's see what he has to say to us now.
Okay, we've been hearing a lot about optical tweezers. Now, I just want to look at some of the very fundamental theory, why it works, and then I'll talk a little bit about approaches we can take to computational modelling, and that will be pretty much it for today. And then tomorrow, some of the details, what you actually have to do to turn the theory into essentially a working computer model, and then finally, what we can do with this. So today, I'll start off with essentially a brief history of optical forces and mix that up a little bit with the momentum of waves, because essentially our understanding of it came out of the history. And I have to talk about some angular momentum, especially since one of the things that we're very interested in is applying torques and rotating particles. And also briefly mention how we actually transfer this to matter. Turns out that the details are not necessarily needed. And then I'll finish up. But it's already been mentioned that the beginning of optical forces was essentially Kepler's suggestion that some kind of emanation, some kind of rays from the sun are responsible for pushing comet tails away. I should mention, Kepler did not know whether or not it was light from the sun or something else being emitted by the sun. These days you might want to think about solar wind and its role in comet tails, and you can see that maybe Kepler was right to be cautious. But essentially he said the sun pushes comet tails away. And the next big player on the stage, I'd say, was Newton. And he wasn't willing to commit to supporting Kepler. He asked, essentially, was Kepler right? And essentially he said, maybe, but I'm not willing to say yes. The other thing we have from Newton is that momentum is equal to mass times velocity. Do we believe that? Was Newton right? Was Newton wrong? Is anyone willing to say that Newton was wrong? From Newton's perspective, waves have no mass, so therefore they can't carry any momentum. Momentum of a wave must be zero. If momentum is simply the mass times the velocity, a wave can't have any momentum. And this idea was taken very seriously. So okay, this wasn't really much of an issue for Newton. He was proposing that light, some kind of particles, a flux of particles. A lot of other people agreed with this. Come the early 19th century in France, we have the arrival of the wave theory of light. Very early on, there were a lot of arguments as to who was right, and one piece of evidence that was given as support by the believers in the wave theory of light was we do not observe any radiation pressure. We don't see any forces exerted by light. Therefore, light must be waves, not particles, because if light was particles, we should see this momentum. We don't see the momentum. There must be none. It must be a wave. Okay, we know already that that must be wrong, but still, that was a fairly popular idea. It didn't last for that long, because essentially, with our early full theories of light, essentially electromagnetic theories of light, we have a succession of predictions that we must have, at least for electromagnetic waves, we must have some momentum, they must exert some force. These are the same thing. You can't have the wave exerting some force unless it carries momentum. If it carries momentum, and we can transfer that to some other object, if we can change that momentum, then we must be able to exert some force. So these are linked. So for electromagnetic momentum, the first would be Maxwell's book. He has about a half-page calculation, basically saying we must have radiation pressure. If a wave's incident normally, then that must carry momentum equal to the power divided by the speed of light. A few years later, that's put on a slightly more rigorous footing by Heaviside and Poynting at about the same time. Poynting gets all the credit. No one could understand what Heaviside wrote. We could complain about this. This isn't general. This is very specifically for electromagnetic waves. We could say, well, I don't believe that this holds for waves in general. This is just something special about electromagnetic waves. But while this was going on, this electromagnetic theory, you had a very parallel development with Nikolai Umov, and he was Russian, Bartoli, who was Italian. Essentially, we're looking at the thermodynamics of moving energy, transferring energy. And essentially, the second law of thermodynamics demands that you must have some momentum associated with that movement of energy. Moving energy must have momentum. Transferring energy from one object to another must exert the force. Otherwise, you find that you're violating the second law of thermodynamics. And it's not that hard to essentially look at a simple derivation of this. Okay, we can take advantage of some hindsight and construct what should be a very simple derivation. And if we consider a mirror, a perfect mirror, no absorption. We have light coming in from the left with some given power, the light being reflected. If this light carries momentum, there'll be a force. Force will be equal to twice the momentum of the incident light. Okay, but this doesn't tell us how much momentum that is. All this tells us that if there is some momentum, then there must be some force. We don't have enough information yet. Well, one problem is that we're looking at this in a very, very special coordinate system. And this is hiding the information from us. So what we should do is look at this in a slightly more general coordinate system. Look at one where this whole arrangement, the two beams in the mirror, they're both moving. Okay, if they're moving to the right, the incident beam is now blue shifted. The reflected beam is now red shifted. If the speed of the motion, let's call it v, is responsible for just this, that's responsible for this blue shift and red shift. What's the change in energy? What's the difference between the incoming and outgoing energy? It's a question. Quick calculation.
H times delta F.
What's the energy of the incoming beam? Well, that's all very quantum. We don't need to even be quantum about this yet. But what's the frequency then of the incident beam? How much is it blue shifted by?
1 plus u is the y.
Yeah? How much is the other beam red shifted by?
1 minus u is the y.
That wasn't so hard. So what's the difference? And that basically is the difference between the power into the system from the beam and the power out of the system. There's no absorption of energy at the mirror. There are no losses in the system. So the only thing that can happen to this is that this is the rate of doing work on the mirror. So we've gotten something useful. We found the rate of doing work on the mirror. How does this tell us the force? Does this tell us the force? Power is force times velocity. We know the force. Why did people spend 100 years not coming up with that, saying that waves must have no momentum? They trusted Newton too much. Well, okay, no, it's a bit more than that. When was energy, in the more general sense, other than just kinetic energy, when was energy as a concept developed? Well, I'd say mid-1800s, but not that much before, essentially, this. So really, this kind of derivation had to wait for the idea of energy.
So when did the Doppler shift? When Doppler was only about that time, wasn't it?
Yes. So it's all of these things coming together. It's really hard to do it from scratch. So we need Doppler shift, we need energy, and ideally we even have the laws of thermodynamics. Once we have that, then it's just a few minutes. Okay, so we can generalise this to light in a medium. Our result before was that the force exerted on the mirror was equal to the power divided by the speed of the wave. Okay, we had c there, but this was just whatever the speed of the wave is. So if we have light in a medium, that's equal to the refractive, that's equal to the speed of light in free space divided by the refractive index. So we can say that the momentum of light in a medium is the refractive index times the power divided by c. Nice, simple, general result. Which brings me to a point that's been mentioned a few times. Essentially, we just celebrated the centenary of one of our older controversies in electromagnetic theory. There was a paper this year where titled the resolution of this controversy. I don't think it'll stop the discussion of it. People have been saying that for about 40, 50 years. Essentially, we can summarise this as Minkowski suggesting that the momentum of light in a medium is equal to what we had before, saying that the radiation momentum is the refractive index times the power divided by c. That was essentially from his space-time version of special relativity, 1907. And very shortly after that, Max Abraham said, no, that must be wrong. And he said, the radiation momentum must be equal to P on C divided by the refractive index. This is different. Is one of them wrong? Can they both be right? Our earlier result, that the momentum of the wave, light wave in a medium, was equal to refractive index times P on C. Is that the same as the radiation momentum? Well, what else could it be? But we can expand this a bit. Both of these really saying that the total momentum is equal to the radiation momentum plus any momentum that the material medium has. And it turns out that for a simple medium where we can characterise everything in terms of a constant refractive index, no such medium really exists either, but we can pretend it does. In the Minkowski picture, it turns out that the material momentum in that case is just completely zero. That's not always true. If you have media with dispersion, non-linearities, things like electrostriction, magnetostriction, it's a bit more complicated. But if it's enough to say, let there be a refractive index, then according to Minkowski, the material medium has no momentum. Everything is electromagnetic. Abraham, however, explicitly confined a number for this. You add these two together, you get exactly the same number. So this is one reason why people are still debating this, because it's not really a question of physics. The physics is on the right-hand side. The physics is what the total momentum is. The total momentum tells us what our total force will be. That's what we will measure. We'll measure the force exerted on some object. We'll measure how much this force deflects a torsion balance. We'll measure the acceleration of some object. This only tells us what the total force is. This whole controversy is about chopping that total force into two parts. One, we can attach a label that says electromagnetic. The other one, we can attach a label that says material. But that's really a question of semantics. That's not really a question of physics. They're exactly the same in terms of predictions. Okay, I can also mention that there have been, over the past century, quite a few papers that claim that there is a difference between the predictions. In every single case where that's happened, essentially there's been some mistake in the calculation of the material momentum. If that's done properly, they come out to be exactly the same total force. So, with this as essentially the theoretical background, it's not that surprising that this was actually detected. So it took a little bit longer, not that much longer. Just on both sides of 1900, apparently Peter Lebedev got there first. He only published in 1901 or so. Nichols and Hull, they very quickly followed. Essentially they used the torsion balance to measure the momentum of radiation. The first claim to have measured the momentum of radiation was de Cook's radiometer, but fairly quickly people realised that that just wasn't correct, because the forces, apart from being in the wrong direction, this is like the little light bulb with the vanes that spin around. Apart from the force being in the wrong direction, they were also about 10,000 to 100,000 times larger than the radiation pressure forces. So it just was simply not radiation pressure. Nichols and Hull, about 10% of their force was the radiometer force. So they managed to reduce it down to a small enough level so they could actually measure the optical force. Sometime later, had a sequence of measurements essentially giving good numbers, good accurate results for the measurement of the total momentum of the wave in material media. So Harvey Jones did this before the laser, repeated it again after the laser, getting 0.1% or so, quite good results. Ashton did this in his early work on optical forces, and essentially they got the same result that we just derived. It's good. Experiment agrees with you. What about angular momentum? Can I just say the angular momentum density is the cross product of the position and the momentum density? Can I just say that? Is this correct? Is it correct? Is anyone sure one way or another? What's an important property of photons? Other than energy and linear momentum? Spin. We know that photons have spin. this statement to say that the angular momentum density is r cross the linear momentum density is essentially saying that there is no spin. It's a statement that there is no spin. What is spin? Okay, from a quantum viewpoint we can say it's some intrinsic property of photons, electrons, whatever. Classically, we can say that spin is angular momentum that doesn't depend on where we choose the origin to be. So we can choose any origin and the spin density will stay exactly the same. This is where the name comes from. We have the angular momentum of a spinning classical object, just a spinning body, and we choose our origin to be at the centre of it. We can calculate some angular momentum. If we choose the origin to be outside, the angular momentum of that rotational motion is still exactly the same. If we're talking fields, we want the spin density to be independent of our choice of origin. And, well, for our expression up there, if we just choose the origin to be at this point, r equals 0, that says I have no angular momentum. It's saying, essentially, I have no spin. So there must be something wrong with this. Okay, as a controversy in electromagnetism, it's 101 years old this year. Dates to 1909. Apparently pointed out first by Ehrenfest, who you saw in the previous talk. So given that this doesn't give us spin, where does spin come from? I don't think there's an easy route to it. If you've done essentially relativistic field theory, you might have seen this. If we take the Lagrangian formulation of electromagnetism, Noether's theorem tells us if we look at the invariance under rotations, then we can find the conserved quantity that we will call the angular momentum. Noether's theorem, it's really, for those of you who haven't met it yet, look forward to meeting it. For those of you who have met it, hopefully you know something about this. It's really a core element, a really central key idea, uniting a lot of mathematical theoretical physics. Essentially it says that if we have a symmetry, we have a matching conserved quantity. So the main ones are because our physics works the same at all points in time. Our physics has a symmetry under translations in time. This means that energy must be conserved. We have a conserved quantity, turns out to be energy. Physics is the same at all points in space. We can make translations, it doesn't affect our physics. This gives us conservation of momentum. Invariance under our choice of direction, just basically saying space is isotropic. This gives us conservation of angular momentum. Conservation of charge comes from gauge invariance in electromagnetism. And if we do this recipe, we find our expression for this conserved quantity has one part that does depend on our choice of origin and one part that doesn't. We can say these are the orbital and spin angular momenta. Okay, there are a couple of minor difficulties with this. And we might ask, can we say, therefore we have an angular momentum density equal to some orbital angular momentum density plus some spin angular momentum density? Sort of. We can't do this unambiguously. Because what our conservation law tells us, it tells us the integral of some certain quantities is a conserved quantity. This doesn't tell me that L plus S, my L plus S densities, that's the actual angular momentum density. This only tells me that the integral of that over all space is the total angular momentum. So I can try to identify the integrand as the density, and that gives us the integrated quantity. But the conservation law does not tell me this absolutely. And it turns out that that integral for any physically achievable case is exactly the same as my R cross P. There's one case when they're not the same. One famous case. It's not physically realisable, but it's very popular as a theoretical construct. Any guesses? Any achievable electromagnetic field that I make will, at sufficiently far distances, sufficiently past times and future times, will have zero fields. It will be bounded in space and time. What famous theoretical construct isn't is infinite, is just finite everywhere, never goes to zero. Yeah, it's an example. In particular, the one that's of most importance here is the infinite plane wave. If you try and calculate the angular momentum of an infinite plane wave, these two will not give the same answer. If you do this for any finite being, they'll give exactly the same answer. For an infinite plane wave, R cross P tells me my angular momentum of a circularly polarised plane wave will be zero. L plus S will tell me plus or minus h bar spin per photon. So that's the difference. But for any physically realisable case, the results are exactly the same. So which one of these do I want to use for calculation? For any real case, they have to give the same answer. Which one looks like it's easier to use? It depends on the case. Sometimes it's easier to use L plus S, sometimes R cross P. If you want to use one and it doesn't work, use the other one. As long as it's not an infinite plane wave. Any kind of finite thing. If you've had the great pleasure of using Jackson as a textbook, he's got about one page of problems that are all about these two things being the same. And we've got some physical basis for saying they're the same. So this is an example from one of the, I think it's one of the better books on this, so the classical field theory. He gives this example to show why these two do really give the same answer. Gives this example of traffic flow in London. Wasn't that orderly last time I was there in London? But essentially, if we have, say, traffic flow around city blocks, he's saying this is our local spin density. If that has a gradient in space, if it's not constant, this is equivalent to having a net flow of traffic. And this is why the R cross P works, because we can replace essentially our gradient of our spin with some transverse momentum. And it's really this picture that gives the same kind of gives the equivalence of these. We see this kind of equivalence quite a lot, especially in electromagnetics. If we have a sphere in a uniform field, we will have some induced polarization per unit volume. You can do the whole problem by integrating this dipole moment per unit volume, or you can replace it by equivalent positive and negative charges on the surface. It's exactly the same kind of transformation. The one thing you don't do is to try and count both at once. You'll be double counting or cancelling, you'll get rather the wrong number. So, if we do want to calculate the spin and orbital components, the simplest way to do this is just to write down the expressions we get out of our Lagrangian recipe. A lot of people don't like this, It depends on our field and our vector potential. And it's because it depends on our vector potential, a lot of people don't like this. They say, no, the angular momentum is a real physical quantity. It can't depend on the vector potential. This must be rubbish. And they go and essentially do this transformation and use R cross P instead. If you look at essentially special cases like a monochromatic wave, this turns out to be independent of the vector potential. You can essentially write this in terms of the fields alone. For a more general case, you can't. So it's argued that essentially this separation in spin and orbital parts is not really physical in all cases. But we're interested in monochromatic fields, and this does work. It's a practical difference too, because if you replace these with the fields, you see that the spin only depends on essentially the intensity and the polarization. So the spin depends on the Stokes vectors of the field. The orbital angular momentum depends on the intensity and the phase gradients. So there's something measurable, physically measurable, we can say is the distinction between them. Okay. Essentially, this is the transport of momentum, an angular momentum by the fields. You can also add transport of energy. It's easy. We just need a pointing vector to tell us that. How are these things transferred to matter? We must actually have some force. We're talking about an electromagnetic wave. And we know, essentially, we've got a fairly simple formula for the electromagnetic force. We usually see the Lorentz force. We have to be careful with this. I mentioned already, we can have this equivalence between our polarization per unit volume. We can have something with no free charge. If there's no free charge, does that mean we can't have any force on it? No, because we have our equivalent surface charges. So if I write down the Lorentz force like this, my charge density there should include my surface charges, the current should include my polarization current. I've made a choice as to whether to use my equivalent surface charges or the polarization. You can write this down in terms of the polarization, and then it's called the Helmholtz force. We can look at the angular momentum. Essentially, if we have a force acting on the matter, moving it, well, the moment of that will give us a torque. But if there's some polarization per unit volume, we have a dipole moment at some angle to the field, there will be a torque acting to align that. So we can add this polarization crossed with the E to our torque. And that has made, with that we've made a different choice about surface charges, equivalent surface charges and polarization. So we have to be a little bit careful with that. Should be consistent with that. So what do we have from all of this? Essentially, we have two different ways we can try to calculate electromagnetic forces and torques. The first, we can look at essentially the fluxes. We can take our object, doesn't matter what object, if we can put some surface around it and calculate the flux of energy, the flux of momentum, and the flux of angular momentum through this closed surface. That must tell us the power absorbed by everything inside that surface, must tell us the force acting on everything inside that surface, and the torque acting on everything inside that surface. How do we know? That's the power absorbed, the force acting on, and the torque acting on our object inside there. When can I know that? What if there were 5 different objects in there? Will this tell me the force on any single one of them? No, not in that case. If there is one object in there, and I know that there's nothing else that will absorb any energy, nothing else that will have a force acting on it, nothing else that will have a torque acting on it, this can be a very simple way to calculate it. There's one nice thing about this. I only need to calculate things over a surface. It's a two-dimensional problem. And remember, this is a lead up to doing essentially computational modelling. I want something that I can calculate. I want something I can calculate quickly. 2D calculations are easier than 3D. And what do I need to do that? Over this surface, I essentially need to know the pointing vector, and if I want to calculate the spin specifically, I want to know the circular polarization as well. So that's essentially my recipe. The alternative, I can just use the Lorentz force law and directly calculate the force per unit volume on the particle. I might have to do this if I can't draw a surface around the object of interest. If there are 5 objects in there, I want to calculate the force on them individually. If I have one large object and I want to calculate the force per unit volume on it, then I need this kind of formulation. One reason why I might want to calculate the distribution of the force on an object is if it's a soft object. If it's, say, a red blood cell, and I want to see how the fields are forming, then I have to be very careful about whether I'm using my polarizations or my equivalent surface charges. Make the wrong choice, I'll get the wrong force densities. But essentially, here's my 2 recipes. The top recipe is usually simpler. Bottom recipe, if my object is very small, so I only need to essentially know the polarization at something that's approximately a point. So really tiny particles. If I want to find the force on an atom, the bottom recipe works quite well. But for a complex object, it's usually harder. And I'll finish this with one further thought. Both of these methods, I need to calculate the fields. So if I want to calculate the forces and torques, my first task is to calculate the electromagnetic fields. These will arise from essentially the interaction of some incident field with my object, and this is really the definition of an electromagnetic or light scattering problem. Incident field interacting with object to produce some new total field. This is the real computational task. So I think I need a break before going on to that.
Questions? Okay. So let's thank the speaker again and let's